Today we're going to be talking about sequential reasoning and Markov chains and hidden Markov chains primarily. And fortunately, Markov chains and hidden Markov chains are just special kinds of Bayesian nets or belief networks. And if you can do the kind of inferencing that last Tuesday's lecture was on, that was a pre-recorded lecture that was posted to the web, then you can do the important kind of reasoning with Markov chains and hidden Markov chains or hidden Markov models. But a Markov chain is essentially a sequence of states like this, or nodes, in which one node depends only directly on the prior node. So state S2 here, node S2 here, is conditionally independent of S0 given its immediate parent. And so the same kinds of rules apply. These are the descendants, S3 and S4 are the descendants of S2, and so knowing the parent of S2, which is S1 in this case, only sort of shields S2 from S0, not from its descendants. So to specify a belief network, we have to specify the usual kinds of probabilities. For the state that's in the very first position, state S sub 0, you've got to specify those probabilities, and then you've got to specify these transition probabilities. What's the probability of S sub 1, a particular S sub 1 given S sub 0? And then we can, again, I've mentioned the independence assumptions here that are made. S sub 3 is conditionally independent of S sub 0 and S sub 1 given S sub 2, etc. But the idea of a Markov chain is that if this is your current state, the only thing that you have to know to reason about the probability of particular state values here is the immediate parent, the immediate predecessor, not the full history of how you got here. And I like this way to put it: the future is independent of the past given the present. Now, when we talk, these are capital S values. These are, in fact, variables, and these variables represent a potentially large number of possible states. And so really what we've got here is the probability, when I say the probability of big S sub 0, this is really a probability distribution, because there's lots of possible states, particular states that this variable S sub 0 can be assigned to. So if I say the probability of big S sub 0, and I say I want to make an assignment to that probability distribution, what I'm really saying is I'm going to assign a probability to one possible value, state value of S sub 0, another possible state value of S sub 0, and so on. And for state variable states S sub 0, I'm going to have some number of states that are valid values of state S sub 0 variable. And for the transitions, I'm going to be specifying, again, transitions between particular states. This is, again, a conditional probability distribution. So for every possible value of S sub 0 and every possible value of S sub 1, I'm going to define a probability there. And there's going to be some maximum number of value assignments for state S sub 0 and some maximum number of value assignments for state S sub 1 in general. And so I'm going to be making these assignments. It turns out that in a Markov chain, Markov model, the assumption is that all these states take on the same possible values. The domain of each of these is the same. So state S sub 0, this variable, I prefer to think of this, and I'm going to probably continue, I'll start talking about this as a step. Step S sub 0 takes on particular state values of, say, in the examples that I'll be using later, X, Y, and Z. And X, Y, and Z are really the states. Step S, or step 0, is a variable for the states that are present or could be present at the very start. But those states, the domain of S sub 0 is going to be the same as the domain of S sub 1, domain of S sub 2, domain of S sub 3. So in a Markov model, the assumption is that this is really signifying the steps, and the state values that can be assigned for each of these steps are in principle the same, okay? The domain of this is XYZ, 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 okay? Those are the actual state values. Each of these steps, again, has a state value, and that state value may be primitive. It may not be decomposable. It may be something like a node in a graph. And if you take a look at the book's description, that's sort of what it seems like. So the examples that they talk about are about robots moving from place to place along a grid, or animals moving from place to place in a cage, or a pen of some kind. And so the intuition is that these states correspond to, there are locations, they are non-decomposable kinds of representations. But in general, each of these state values can be a joint outcome, if you remember the probability lecture. This would be a permissible state value for any of these states here. This might be a permissible state value. So in one domain, like the robot delivery system, this would be a state value for perhaps one of these states, just like it was in the planning lecture or the planning material. Another possible state value here might be again, a joint, a member of a joint outcome space. It might be a vector that looks like that, of the kind that we studied in machine learning. And so states in general are not necessarily going to correspond to primitive nodes that are not decomposable. They are typically going to correspond to more complex kinds of knowledge structures that are themselves represented by features. And we would typically then talk about how to represent those. And let's see, I'll come back to that later. But so strip styles operators of the type we define there talk about effects. The planning operations that we talked about in chapter 6, in some ways are trivial kinds of Markov models, because the probabilities are rather trivial, but in those models that we talked about in chapter 6, we might have states that satisfy certain preconditions, and if we apply an operator, we get an effect. And the assumption is that we get the effect with certainty. So with probability 1 in the chapter 6 assumptions, if we are in any state that satisfies this condition, then we will go to another state with probability 1 that satisfies the condition given in the effect. And so we might have a probability transition functions like this, in which the prior state is defined one way. This is actually a class of prior states. The ... can be filled in multiple ways. And the probability of getting a new state, given this prior state, is fixed, okay? Now, this assumes that, in this case, this probability of one state given a prior state, the probability equaling 1, is true if I apply the pick up coffee operator. I'm jumping ahead briefly because we haven't talked about actions with respect to Markov models yet. But pick up coffee is an action, and you can just remember that for later in the lecture. But if I was just observing the world, and if I was just looking at the behavior of a robot in the world, and I was simply looking at the states that were being enumerated, described this way, this is what I was immediately observing, and I had no way of necessarily immediately observing the actions or the operators of the robot, then I might, over a large number of observations, decide that the robot is executing this transition, or this transition is happening between a state that is of that form to a state that is that form, say 30% of the time. Because the robot might be in this state sometimes and not apply this operator. Why might not they apply this operator that goes from here to here, pick up coffee? Because Sam may not want coffee. And so observationally, this is just a, if you look at these slides later, don't get thrown by this 0.3. I just made it up, okay? Just made it up. But the point is that the material we talked about in chapter 6 is largely a Markov model with very degenerate probabilities. The assumption is that every time you make a move, the outcomes are certain, as defined by the strips operators. A couple comments here that I think are important. What if the future does depend on the past, as well as the present, where past corresponds to the past in the present state? Back here, I decide to apply, if I were a robot, I might decide to apply an operator regardless of how I got to a particular state. I don't care the path I got to a particular state. I can go ahead and apply that operator. And so in that case, in that simplified domain, the future only depends on the present, not the past. But I might be, for example, in downtown Nashville, and I might be down there for a variety of reasons. I might have gotten there by a variety of paths. I might be on my way home from a trip, or I might be down there shopping. And in this particular case, what I am going to do when I'm at a particular location, let's say we define state as location, probably is going to depend on other things besides what I am saying is my state description. I'm going to be basing my decision on goals that I might have. I'm going to be basing my decision on, or my behavior rather, is going to be based on the way I got there. If I happen to be driving through downtown because I'm coming back from Elizabethtown, Kentucky, it's clearly I'm on a trip and I'm on my way home, and I'm going to go flying through any intersections or interstates that I approach. But if I'm going down there shopping, or if I'm going down to visit the Central Library, I might find myself at the same intersection I flew through under other conditions, and I might behave very differently. I might take a left turn into the library parking lot, for example. You know, the kind of classic example that's often brought up when talking about non-Markov processes is historic long-time grievances between populations that have persisted over the years, and it's never the case that it simply doesn't seem to follow a Markov process. You can't simply do a reset. There's too much history there. So what if the future does seem to depend on the past in the way that we're talking about here? And we're thinking about the past, again, as in a very simple way. It is a path. I'll fix that typo. It's a path to the present state. So in our planning system or in our search material, we talked about looking for a path of getting from the start state to a current state. And that path was in some cases very important because I was basing the optimality of the solution on the path and not simply, in some cases, the state. So here is a representation of, let's say this is what I mean by the state, maybe an intersection. And this is the path from the start state to the state that I'm currently considering here. Processes that don't have the appearance of being Markovian can be translated to a Markov model in many cases through a sort of trivial re-representation. We can still take a problem that doesn't appear to be Markov and we can make it Markov in this slightly revised space. So what a state becomes in this slightly revised space is it's a state that, as I interpreted it earlier, but I add the path of getting from the start state to that state as part of this augmented, new, more complex state representation. And now I can look at this current state, and because I've embedded the path to what used to be the interpretation of the current state, I have access to the past. I have access to history. And so I can do this translation and ensure that, one, in this state representation, I have a Markovian process that is informed by the past. The only point there is that the Markov process is not as limiting as you might think, because I can do tricks like this. This could get pretty expensive. Now, the generic algorithm, search algorithm that we've been talking about, in fact, stores paths with states. And so it uses this representation already. It uses it not so much because it's trying to maintain this Markov property, but because it's using that path information to make judgments about the optimality of the path, the cost of the path, and some other things. And because typically it's going to be something that the path is going to be something that gets returned when it finds a goal state. But anyways, it's also a trick for converting a problem to so that it has a Markov property. But there is a big cost associated with it because the cost necessary to store all those paths is potentially exponential depending on the other choices you make in your search algorithm. What if the next action also depends on the goal? What if I'm trying to go home versus get to the library? Well, I can embed this other information that I think is important in making judgments about what I do in the state description. And so the goal that I'm trying to pursue can become part of the state description as well. And so, in looking at a real problem, we often might craft it in a particular set of ways. So a stationary Markov model is essentially when the transition probabilities don't change over time. If you take a look at the transition probability specified here, the transition probability from S sub 0 to S sub 1, states here to states here, are going to remain the same over time. And likewise, the transition probabilities, remember, I'm thinking of these variables now as steps, but really their domains are states. The domains here are states. And the probability of going from a state here to a state here is the same as going from the same state in S sub 1 to the same state in S sub 2, the corresponding states in S1 and S2. So when I specify the transition probabilities, or when I specify the Markov model in a stationary Markov model, I have to specify the probabilities of the states in S sub 0. And that's because of the definition of a Markov model. The probabilities of the states in S sub 0 is going to be the same as the probability of the same states in S sub 1. And then to define the transition probabilities, I just have to define the transition probabilities from here to here. And because those are going to be the same, so the transition probability when S sub 0 equals X to S sub 1 equals Y is going to be the same as the transition probability for the case where S1 equals X to S2 equals Y. So I don't have to specify nearly as many probabilities as you might think, because the probabilities are going to be the same across the different, transition probabilities are going to be the same across the different steps. So it's easy, it's often natural, and you can extend the network indefinitely. We can extend this network into time forever under the stationary model, and it's not going to require that we specify any new numbers for that extension. So here's just a simple example of stationarity. The probability that the robot is in the lab, the robot has coffee, Sam wants coffee, and then information about mail given, information that's very like that, except the robot does not have coffee in this predecessor state. The probability of making this transition is, let's say, 0.95. And it's 0.95. The transition probability between these two states is 0.95 at step 2, step 23, step 10,037, every step along the way. Okay, so that transition probability will never change, and none of the transition probabilities will change. Now, in a situation where actually the robot is doing some learning, it's not going to be the case that we have a stationary system, or at least we hope it's not going to be the case that we have a stationary system. The environment might change in various ways. That's one way you can alter stationarity, but the robot itself may change. And so this transition probability for a robot that's being trained, when Sam wants coffee and the robot doesn't have coffee, the robot early in training may, this transition probability may be quite low for the untrained robot. But as the robot goes through training, and I'm not elaborating how that training is done, the transition probabilities of going from here to here, because of the robot's actions, the robot's cognitive capabilities are changing, is going to change. And so we hope that if Sam wants coffee and that's the robot's goal to satisfy Sam, then this transition probability from this state to this state is going to increase with training. So these are non-stationary stationary dynamics. In this particular example, because we're actually changing the robot through machine learning. But in other cases, it may be that the environment's degrading. Operations that are performed in a pristine environment before a hurricane are going to be different than operations, the transition probabilities that are going to be true after the hurricane. The environment is going to change. And so there are lots of situations in which the stationarity requirements are not necessarily satisfied. Just some terms. You can read these. I'm most concerned with this one. In a Markov chain, all states are reachable from other states. There is some non-zero probability of going from any pair of states in the system in a true Markov chain, Markov model. The book has an example of PageRank in it as an example of a Markov chain. And this is part of Google's original search engine. I remember when it came out, it was all the rave. But in this case, the steps are going to correspond to web pages that are visited at different times. And the model is based on an assumption that the web pages are equally likely at 0 here, but and we have they're just going to be defined this way, where n is the total number of web pages. So the probability of S sub 0 being at a particular state or a particular page is going to be 1 over the total number of web pages. That is an assumption. And then there are transition probabilities of moving from one page to the next. And this is the way that the transition probability is defined. There is a D parameter here, which is basically a parameter that specifies how likely it is that the user will, at each step, continue to browse. Very often, D seems to be the default, in most cases, seems to be 0.85. Once you start browsing, apparently, it's a reasonably high probability you'll continue to browse. You get lost in browsing. You can read more about the history of PageRank here, and it goes into some more details about why this parameter was chosen. But the probability that a user will continue to browse, if they're going to continue to browse on the next step, if they are at a particular page, P sub k, at one point, we want to predict the probability that they'll be at another page, P sub j, on the next step. So the probability they're going to continue to browse, and these are essentially probabilities that they will actually move to this page, P sub j, under different circumstances. So if P sub k actually links to P sub k actually links to P sub j, there are links from this page to this page. The assumption is that the user will take one of those links when browsing. And so this is simply 1 divided by the total number of outgoing links from P sub k to any page. And some fraction of the time, the user will choose to go to a particular new page, P sub j. If P sub k has no links, then the assumption is that the user will just choose randomly another page anywhere on the web. Not reasonable, of course, but just an assumption that was made early on. This assumption has probably been dropped long ago by Google. And this assumption probably now is, this has been replaced by, in fact, both of these have been probably revised to take into account common thematic relationships between, not explicit links, but thematic relationships between prior pages and next pages. And in the early version of PageRank, if P sub k did have some links out, but one was not P sub j, then with probability 0, you would actually go to P sub j. So the assumption here is strongly biased towards going to pages that are linked out of or linked from the current page. This is a bit less intuitive, but I characterize this as, so this is the probability, you can think of this as the probability that they're going to be following some kind of connection. There's going to be some kind of way to informing the browsing. I characterize this as sort of the the probability of a mental break. You just completely switch topics, and you choose amongst with some probability, you just choose amongst all the pages on the web. In some places, I've not seen this term discussed, and in fact, in the original paper that discussed PageRank, this term was actually written out differently. So it is a kind of non-intuitive term, I think, but you can think of this as a Markov model because it defines the transitions from one page, or each page to another page.